set up a certain rules. So that's the definitions. So we define some definitions. That's, you can define anything you want because it's definition. Definition has no true, no wrong in it. It's just like you play a game, right? You set up certain rules. The rules, to one person may be right, to another person may be wrong. So we don't care about if the rules are right or wrong. There's no right or wrong to the definition. Definition is the definition. It's just like my name, right? My name, my parents named me Chen. There's no right or wrong to my name. I'm just given the name Chen. So that's a definition. Based on those definitions, right, we may make some logical, relations. Then we try to prove a theorem. So theorem stands upon definitions, right? So definitions have to make sense. Definitions have to make sense. There's no right or wrong to it. It have to make sense. Then the theorems are proved based on the type of definitions. Okay, here are some examples of theorems. So intermediate value theorem. Let's review that. If f is continuous function on an interval or closed interval a to b, and n is any number between f of a and f of b, where f of a not equal to f of b, then there is a number c in the set of a from a to b. Well, we don't want c to be a or to be b, so that's why a and b are excluded, such that f of c equals to this n. All right. So theorem, let f be a differentiable on an open interval I. So I is any interval, right? You can think as an interval from a to b. And let a number in this interval. So c, let c in this interval. If f of c is the maximum or minimum value of f on this interval, then f prime of c equals to 0. Right? That means there's a certain point there, and its a tangent line is parallel to x-axis. Let's see some propositions. Suppose x, y is in the integers. If x and y are odd, then x times y is odd, right? We can prove this. Proposition, let x and y be positive numbers. If x is less than or equal to y, then square root of x has to be less than or equal to square root of y. Or proposition, the function f of x equals x cubed plus x is an odd function, right? You saw those three propositions. Those three are can be proved easily. So it doesn't have such a big weight or heavy weight in mathematics. So theorem like an intermediate value theorem. So it's a heavy weight. So it's like a series. So it's called a theorem, right? Because it takes a little bit of effort to prove. Okay, anyone has any questions so far? So we're talking about the 4 kinds of proofs to prove a theorem. We're going to be cover them later on. And usually, right, we call a theorem, theorems are proved upon the definitions we set up. And less important theorem we call propositions or lemmas. And from a theorem or proposition or lemma, sometimes something is obviously true, we call it corollary. Anyone has any questions? Okay, let's go to the definitions. All right, thank you, Patrick. In order for our proofs to be unambiguous, So all the terms we use must be established. That means we have to make definitions. So we have already established the terminology of sets, right? Sets, lists, statements, and all those symbols. Right? The first two symbols means the element in or not in a set. And those two symbols means a subset, is a subset or is not a subset, right? So those two compares sets. And these two see element and a set. And the number system, we use these 4 letters. So this double line N means natural numbers. Natural numbers, counting numbers. The second one, Z, integers. Q, rational numbers. Right? R, real numbers. Now to prove some simple statements, we must establish the exact meaning of the term, like odd integers, even integers, divisible by, or prime, or odd function, or even function, so on and so forth. So theorems is proved upon definite definitions. Okay, let's see some definitions. Now integer n is even if n equals to a for some a in integers. All right? So that means if a number is an integer, we can write, if a number is even, we can write as 2 times an integer. Right? 2 times an integer. Now integer n is odd if the number can be written as 2a plus 1. The a represents any number in the integer. Okay, so usually, for even numbers, we write as 2a, and a is an element in the integer. For odd number, we write as 2a plus 1. Right? Normally we use 2k plus 1. This definition, suppose a and b are integers, we say that a divides b. So a divides b means this. We written as this notation, a bar b. So that means a divides b, like a 4 divides 2. Okay, which also means b equals to ac for some c in the integer. In this case, we also see that a is a divisor of b. A divides b. Think about 2 bar 4, or 3 bar 6, or 2 bar 6, 3 bar 6. So remember we talk about factors. Maybe it's more more familiar seeing factors. 2 is a factor of 6. 3 is a factor of 6. But this we just change it. We see it differently. We see a divides 6. 2 divides 6. 3 divides 6. And that b is a multiple of a, right? So think of 6 is the multiple of 2. 6 is multiple of 3. So we use this notation, the bar notation. So 2 divides 6. A divides b. A is a divisor of b, or a is a factor of b. A natural number n is prime if it has exactly 2 positive divisors, 1 and itself, right? That's why the first prime number is 2, it's not 1, because 1 has only 1 divisor, right? So the definition of prime saying it has exactly 2 different divisors, 1 and itself. A function is called even function if f of negative x equals to f of x. Yeah. think about x squared. F of x equals to x squared. That's an even function, right? Because we have x squared, so negative x squared is also x squared. A function is an odd function if f of negative x equals to negative f of x, right? Think about the identity function. F of x equals to x, right? That's a straight line past the third quadrant and the first quadrant. So that's, identity function is an odd function, or x cubed. X cubed is an odd function, because if we plug in negative x, we get a negative x cubed, which is a negative f of x. Certain facts from arithmetic and algebra are, accepted as true, which means, we take for granted, right? For example, the ordering of numbers and commutative, associative, distributive properties of algebra. Later, we will show certain properties from terminology. So we may assume certain established facts about trigonometric functions. All right, so this is talking about, make definitions, right? Make definitions. And definitions has to make sense. All right, now we have 4 kinds of proofs. Let's talk about the first kind of proof, direct proof. So if P, then Q, or P implies Q. Let's see this one. Proposition. If x is odd, then x squared is odd. So how do we prove this? P is x is odd, right? P implies Q. Q is x squared is odd. So we want to show P implies Q. So we start by assuming P. All right. If part, we always will assume P. We want to prove Q is true. So which in this case we'll assume x is odd, right? X is odd. Then we prove x squared is also odd. Remember we said odd number we can write as 2a plus 1, right? So we'll assume this x can be written as 2a plus 1. Then we calculate x squared. So x squared equals to 2a plus 1 squared equals to 4a squared plus 4a plus 1. Then the first 2 terms we can write as this, 2 times something, right? 2 times something. So 2a squared plus 2a plus 1. You see, this is in the form of 2k plus 1, right? So this in the form of 2k plus 1. So this shows us this is an odd number. So x squared is odd. So x squared equals to 2b plus 1, where b is an integer, 2a squared plus 2a. Well, actually, b is an even number, we can see from here, right? So by definition of odd, right? Odd means it's 2 of something plus 1, right? Something is in the set of integers. That's the definition of odd number. Then x squared is odd because x squared can be written in the form of 2 of something plus 1, 2b plus 1, and b is an integer. Okay, this is a very basic proof. Does anyone has any question with this? So this is direct proof. We assume P, we derive Q. Let's see this proposition. Let A, B, C be integers. If A divides B, so if A is a factor of B, A is a divisor of B, and B divides C, that means B is a divisor of C, or B is a factor of C, then A is a factor of C, or A divides C. All right. So let's see. Question. Is it enough to say since 3 divides 15 and 15 divides 60, this implies 3 divides 60? Hence, the proposition is true. We cannot do that, right? This is just one case. Right? This is just for one number. So no, it's not, because we have shown a particular instance. So that's not enough to be, this is not enough to prove for A, B, C for any integers. This is just a typical example. So this is not a proof. To prove, we have to use the definition, right? If A is a factor of B, that means B can be written as AS. S is an integer. B divides C, that means C can be written as BM. M is an integer. So from there, we prove A divides C. So let's see first step. So we still do P implies Q. So it's still direct form. So we assume A, B, C are integers. We assume A divides B, B divides C. Then we want to show A divides C. Right. So by definition of divisibility, so A divided B means there's a D in integer, such that we can write B as A times D. Similarly, for B divides C, that means there's E in the integer, such that C can be written as B times E. Then C can be written as B times E, but B can be written as A times D. So C can be written as ADE, right? Then we see A is also a factor. You see here A is a factor of C. So that means A divides C, right? Or C can be written as AF for F equals to DE. We don't really need to do that step, right? This is enough. So this step here, this is the show. So A equals to A times, no, C equals to A times DE. This is enough to say A is a factor of C, or A divides C. A divides C. Okay, anyone has any question for this proof? All right, good. Let's keep going. So there's some direct proofs require a little bit more creativity in some steps. Let's see this one. Proposition, let x and y be positive numbers. If x is less than or equal to y, then square root of x is less than or equal to square root of y. Right? We may not, again, to use one number to prove that. All right? No. So we want to prove for any positive numbers. When we talk about numbers here, we're talking about real numbers. All right? Positive real numbers. So we suppose x is less than y. Remember, this is if P then Q form. If P then Q, we always assume P. So we assume x is less than or equal to y. Right? Then subtract y from both sides, we get x minus y less than or equal to 0. Right? And x and y we can write as this. X squared square root, because square and square root cancel each other, right? Y can be written as y squared square root. So it can be written in this new form. And then remember there's a difference of two squares, right? Difference of two, this is the difference of two square form. So we can write as this. Square root of x minus square root of y times square root of x plus square root of y less than or equal to 0. because we want to show square root of x is less than or equal to square root of y. But we see this one. We see square root of x plus square root of y is always non-negative, right? It's always non-negative. It could be 0, right? Square root 0 would be 0. Square root y would be 0. So this is positive. It's not right. It's non-negative. Right? It doesn't have to be positive. It can be 0. So it's non-negative. So here, actually, we should divide it into 2 cases. Right? We can divide it into 2 cases. Okay. You know what? This is true. Because we assume x and y are positive numbers. So we omit 0. We omit 0 from the beginning. So we don't want x, y to be 0. We assume x, y are positive numbers. So that's why square root of x plus square root of y is positive. So we can divide it on both sides. So when we divide on both sides, 0 divided by a positive number, still 0. So we get a square root of x minus square root of y less than or equal to 0. Then we move, we add square root of y on both sides. So we prove of Q. So we assume x, y are positive numbers. We assume x is less than or equal to y. And we used some mathematical skills. We showed square root of x less than or equal to square root of y. Anyone has any questions for this? Okay, that's why sometimes we need to think about how do we use some mathematical skills or properties, right? Here we're using difference of 2 squares to write as a factor. Okay, let's see another proposition. The function f of x equals to x cubed minus 4x is odd. Right? Remember the definition of odd functions is f of negative x equals to negative f of x. So we want to show that. So we want to plug in negative x into this function. So we would get negative x cubed minus 4 times negative x. We simplify, we get negative x cubed plus 4x. So we factor out the negative sign. We get x cubed minus 4x. Well, x cubed minus 4x is just f of x. So we showed f of negative x equals to negative f of x, which is the definition of odd function. To show a function is even or odd, we just plug in negative x into a function. Another example we can use is for some trigonometry identities. Let's see this one. So tangent x, so by definition, tangent x equals sine x divided by cosine x. Cotangent x equals to cosine x divided by sine x, or 1 over tangent x, right? Cotangent and tangent are inverse with each other. Cosecant x equals 1 over cosine, so cosecant, oh no, this is wrong. Cosecant is sine, this is type O, so this is not cosine, this is sine. Cosecant x equals 1 over sine x, all right? Cosecant and sine are inverse with each other. So this is type O. This is sine x. Secant x equals 1 over cosine x. So secant and cosine are inverse with each other. And then we have one identity, sine square x plus cosine square x equals 1. So this is a Pythagorean theorem in trigonometry functions. So let's see, we have this proposition. We want to show tangent x plus cotangent x equals to secant x times cosecant x, right? So we want to prove the 2 sides are equal to each other. We can go from left-hand side, arrive at the right-hand side, or we can start from the right-hand side, arrive at the left-hand side. Or sometimes maybe we maybe we simplify both sides, meet in the middle, which means the left-hand side equals to something, and the right-hand side also equals to something. All right, so there are 3 kinds of ways to do this. Let's show this one actually. Proposition, it doesn't. So tangent plus cotangent, we want to show tangent plus cotangent equals to secant times cosecant. Well, let's do on the whiteboard. So we want to show tangent x plus cotangent x equals to secant x times cosecant x. Okay, so this is our goal. So tangent x plus cotangent x, which is 1 over tangent x, right? Tangent x. We can simplify this. How do we simplify this? We can combine those 2 terms, right? Tangent x, oops. Tangent x, we can multiply tangent x times tangent x over divided by tangent x. So the tangent square x plus 1, then divided by tangent x, right? Because we need a common denominator. The first tangent x, which need to be tangent square x divided by tangent x. Once we have common denominator, we can combine the numerator. So we get a tangent square x plus 1. What's tangent square x plus 1? That's a secant square, right? That's a secant square x divided by tangent x. We have this. So do you see we're getting closer, right? So now tangent x, so secant square x divided by tangent x. Remember, tangent x is sine over cosine. So divided by it is the same as multiply by cosine over sine. Oops, I'm missing x. Right? Then just leave 1 secant x on the side. Right? So because on the right hand side we do have a cosine, we have secant x. You see the rest of it, we have a secant x times cosine x divided by sine x. That's simplified to be cosecant x. Oops. All right. So this proves going from left-hand side to right-hand side. You also can go from the right-hand side to left-hand side. All right. Okay, anybody has any questions so far? You can always stop me to ask questions, all right? Okay, now using cases. So sometimes in a proof, we need to divide the problem into several cases. We prove the statement separately for each case. For example, if we want to prove something for all natural numbers, we can divide the proof into 2 cases, odd numbers and even numbers. Right? If we want to prove something for all integers, we can divide the proof into negative case and non-negative cases. So let's see this proposition. If n is an integer, then 3n squared plus n plus 14 is even. Right? Remember, in integers, we have positive integers or negative integers or odd integers and even integers. So here we're going to divide into two cases. We will consider odd case and even case. So case 1, n is odd, right? If n is odd, we can write n as 2k plus 1, and k is an integer. Then we just put 2k plus 1, substitute this n. So we do the calculation. So in the end, we still get this. Yeah, we go through the calculations. So we have 2k plus 1 squared plus 2k plus 1 plus 14. We simplify, we combine like terms. In the end, we get 12k squared plus 14k plus 18. We want to show the result is even. What's the even? Even means we can write as a 2 multiplied by an integer. So we factor out 2. So this number, the result can be written as 2 times something. And this something obviously is an even integer, right? So that's how we prove it. As long as we can write the result with 2 times something. 2 is a factor of it. So that's to use the definition to prove is the result is even. So the result is even because 2 is a divisor or 2 is a factor. Case 2, n is even. N is even, that means n can be written as 2k, right? We go through the same process. In the end, also we can write the result as 2 multiplied by an integer. So 2 divides this result. That means the result is an even. So here we divide into two cases, n is odd, n is even, to prove both cases. Sometimes treating similar cases. Sometimes if certain cases are similar, we don't have to write them out separately, for it will become too redundant and tedious, because before the next proposition, first we have a definition. So let's see definition. Two integers have the same parity. So we will see what is parity. If they are both even or both odd. Otherwise, they are having opposite parity. Okay. So same parity means even the both odd or both even. Opposite parity means one is even, one is odd. Proposition. If two integers have opposite parity, then the sum is odd. Think about 2 and 3, right? One is even, one is odd. 2 plus 3 is 5, is odd. So think about two even integers. 2 plus 4, that's 6, 6 is even. Now think about the two odd numbers. 3 plus 5, 3 plus 5 is 8, even numbers. So only when the opposite parity numbers adds up to be odd. Okay, Moises, does the order matter when writing more than one case? No, does not matter. Maybe in some crucial cases it matters. Let's say sometimes we want to prove for non-negative, right? If let's say we want to prove for non-negative, that means we have to prove to be the case for 0 and case for positive. So maybe we always prove for 0 first. Yeah, maybe only sometimes. But in this case, doesn't matter, prove to be even, to be odd, doesn't matter. Okay, let's prove this proposition. Two integers have opposite parity, the sum is always odd. So we assume one number is even and one number is odd. The even number can be written as 2 times something, right? And the odd number is 2 times the integer plus 1. Then when we add those two numbers, we see the two numbers, the sum can be written as 2 of something plus 1, which is in the form of odd number. So then suppose, the opposite. M is odd, N is even. So these two cases you see is similar, right? Just assume one is odd, one is even. Do we really need to do these two cases? Not really, not at all. Because why? Because addition is commutative. It doesn't matter which one is odd, which one is which one is even. So in either case, m plus n is odd integer. So you see in these two cases, there's no need. Those two cases are similar case. There's no need to divide into case 1, case 2. So sometimes we use this sentence to represent that without loss of generality. So usually we take as a shorthand. We abbreviate it as WLOG without losing of generality. All right, WLOG, because to prove the two cases are very similar, we use this WLOG. Okay, let's something more on direct proofs. Sometimes in calculus, you are asked to show or prove certain things directly using the definitions, rules, or laws that you were given. In these examples, we were given definitions of words like odd, even, divide, multiple, and parity, and asked to prove various propositions using the definitions. Earlier, we saw definitions of odd function and an even function, and asked to use them to show various functions odd or even. Other cases like computing a limit, use a limit law. For example, we want to prove limit x approaches infinity, then with this rational function, right? If we remember that, how to do that, remember something called ignore rule. We take the leading terms. So this shows the range of the function, right? When we take a limit, let x run to infinity, that's to find out the range for this rational function. How do we do that? We take the leading term of the numerator, we take the leading term of the denominator. The leading term of the numerator is the square root of x squared, which is just x, right? Then the limit of this whole thing is the same as the limit of the leading term in the numerator, which is x, divided by the leading term in the denominator, which is also x. X divided by x, which is 1. So basically, the result of this equals to 1. So limit of this equals to 1. Basically saying, okay, what's the range of this rational function? The range of this rational function is any real number, but not 1. But not 1, because 1 creates horizontal asymptotes. Okay, use the definition of derivative to show the derivative of a function, right? If f of x equals x cubed, then f prime of x equals 3x squared. This is by applying the shorthand rule of taking derivatives. Same thing for this, right? This is called the power rule. If f of x equals x raised by n, then f prime of x equals n times x with power of n minus 1. Oh, okay. And I finished the lecture notes. I was worried if we cannot finish all those. Okay, so far, any questions? If no questions, we're going to the classwork. Anybody has any questions? Did I do too fast? Okay, I try to see in the last example. Last example, which example? This one? This one, two integers have opposite priority, adds up to be odd. 6. Oh, okay. So this is in, okay, the previously we already see we use odd, even, divide, multiple, parity to prove. Also, we proved about odd function and even functions, right? This is saying that more can be used. What are some more can be used? Like limits, right? Remember, how do we prove the limit of this equals to 1? We use a certain limit laws, limit properties, right? And also for this, how do we prove this? We use the derivative laws, right? How to take derivatives. Remember, this is proved by power rule in differentiation. Does that make sense? Basically, 6 means that more laws, properties in mathematics can be used to prove things. Okay, all right. Okay, let's see some classwork. One, two, three, four, five. No, we've done this already. 8. Okay. So let's prove those propositions. Do we have to add the box icon at the end of every proof? Oh, yes, the square, right? Right, usually the square on the bottom to tell people, okay, this is the end of my proof. Thank you. Some people use two slashes to represent that. Right, we use a square on the bottom. It's like a period for proofs, saying, okay, this is the end of the proof. Thank you. Okay, let's prove this. Let's prove these 3 propositions. Actually, we did in the class already, right? But just read out yourself. All right, let's see. Oh, Nino, in the lecture, we already mentioned we cannot use one particular number to prove. This would not be a proof, all right? A proof, we have to use the definition. What's the definition of an odd number? The definition of an odd number means x can be written as a 2a plus 1. We have to use the definition to prove. Use one number is not a proof, all right? We have to use definition to prove. Great, I'm looking at Samuel and Moise's proofs. Yeah, looks good. Use the definition to prove, okay? Mathematical theorems, proof of theorems have to use definition. We cannot use a particular number to prove. Use a particular number is just showing one case. We want to show it works for all numbers. Okay, 2 more minutes for the first question. Yeah, the if part we always assume. So assume x is odd. You know, if p, then q. P part is always assumed. Shamisha, you have to expand 2n plus 1 square. If you only write x squared equals 2m plus 1, that's not enough. All right? You see, if you let m to be 2m plus 1, you only have m squared. You don't have 2m plus 1. Shamisha, do you see that? You only have m squared. You just change x to be m. That doesn't change anything. You have to expand 2m plus 1 squared. Michael, you're missing 2. You're missing 2 for a squared. Jinqi, that's not a proof. Right. Okay, you haven't finished, right? You're just writing P. You suppose P. Assume P part. Yeah, Maria is good. Right, Xiaomi is good. Michael, you're missing 2 times 2a squared. You have 2 as a coefficient of a squared. Okay, what about Aidan, Ajaya, Ishrat? Yeah, that's A part, right? That's P part. Remember, direct proof is if P, then Q. The P part will assume P. Right, Michael, yes. Right. That's right. He's right. He's right. I don't know. I done x squared equals 2a plus 1 squared. Now we have to, oh, right. You didn't finish writing. Right. 4a squared plus 4a plus 1 equals 2 times 2a squared plus 2a plus 1. Yes, it cut off. Okay. Yes, that's right. Yes, Jinqi, that's right. What about my? I didn't see your answer. And okay. George is not here, huh? We're missing George. We're missing Dayong today. All right, what about C? Function f of x equals x cubed minus 4x is odd. I'm going to change exactly same. Right, let's change it to be f of x cubed. Let me write here. So f of x equals to x cubed minus x. Okay, it's even easier. Do this one. So show this function is odd. Okay, Samuel, you made yourself adding So your function is f of x equals x cubed plus 4x. That's also odd function. That's right. That's right, Shamisha. That's right, Maya. And then what happens to the 4? Oh, because that question is exactly same as the lecture notes. So I change it to be f of x equals x cubed minus x. You can do minus 4x as well. Right, Mai Wu, yes. Xiaomi, yes. Good. Right. Okay. The rest of the questions, I'm going to call people to show. I'm going to call on your name to show. Okay. Okay, D. I'm going to give D, E, D, E. We have two questions, D and E. I'm going to give you 3 minutes to do this. Then I'll call on people to show this, okay? And then x cubed minus x of negative x cubed plus x of negative x cubed minus x. Right. And then you need one more step, right? To see f of x, f of negative x equals to, yeah, equals to negative f of x. You need to make the conclusion. Yes, that's the conclusion. This is the definition of odd function. Okay, great. Okay, let's do E, D, and E. Let's prove D and E. Let me give you a couple minutes. Then don't type. You don't need to type in your answer in the chat. I'm going to call you. Okay, I'm going to call on people to show. Okay, Jaya, can you show D? You can explain, you know, if it's too difficult to type in, or you can share your work. Okay, not done yet. All right. Let's see, Maria. Okay, Maria, this kind of proof, we need to write only one side. We can start from left-hand side, then we arrive at the, we can start at the left-hand side, arrive at the right-hand side. Let me see. Oh, you're still working. Okay, you're still working through it. I see. Let's see. So, Nino. Okay, cosine x does not equal to sine x divided by 1, right? Anything divided by 1 is just itself. And the cosecant x, you want to write equals to 1 divided by sine x, not sine x divided by 1. And the secant equals to 1 over cosine. Cosecant equals to 1 over sine. Okay, my Wu, do you? Okay, you cannot write both sides at the same time. To prove this is to go from one side to arrive at another side, or both sides arrive at the same spot. So let's see. So you change tangent x to be sine over cosine, cotangent x to be cosine over sine. Then this equals to, oh no, you cannot do this. Do you see what I mean? You go one side to the other side. You start from left-hand side. You want to simplify left-hand side. In the end, you want to arrive at the right-hand side. You cannot do both. If you want to do both simultaneously, you cannot write equal sign in the middle because you need to prove they equal to each other. Does that make sense? You want to start from one side, right, end up at the other side. Or you can simultaneously simplify both sides, arrive at the same thing. Let's say each right has tangent x plus cotangent x, sine over cosine plus cosine over sine. That equals to, we need a common denominator. So common denominator is sine cosine. So we have sine squared plus sine squared plus cosine squared. I think you're missing square, right? Divided by cosine times sine. Then sine squared plus cosine squared equals 1. Good. So 1 divided by cosine sine. Well, 1 over cosine is secant, 1 over sine is cosecant, equals to right-hand side. Great. Yeah, this works. This works. Yeah, there are different ways of doing this. All right, anyone has any question for this one? All right, let's show E. E, right, we have time. So E, we want to prove this function is even. Oh. Let's see, we're back to Ajaya. Do you think you can you show this function is even? Oh, I see. Okay, Michael? Okay, I guess, Sammy, your question is still over the trigonometry functions, right? Sometimes you see this one is easy to go from left-hand side to right-hand side, or it's not also difficult. It's either difficult to go from right-hand side to left-hand side. But sometimes you see both sides are very difficult ones. So you want to simplify both sides to a simpler one. Or E. E, use the definition, right? What's the definition of even function? F of negative x, use the definition, f of negative x equals to f of x. So we substitute negative x into the function. If that equals to f of x, that's how we prove it's an even function. Oh, okay. I don't think I answered Samuel's question. Samuel's question is why we need cases. Because otherwise, how do we prove it? Because we want to prove this n equals to this n is in the integers, and we want to prove the whole thing is even. Because in the integers, we know there are integers to be odd, there are integers to be even, right? That's why we need to split into two cases.
Professor,
Yeah.
when we use cases, we're just using a couple integers to prove that it's even?
No. We use cases, we use even integers and odd integers. How do we write even integers? We write n equals to 2k, right? Odd integers, we write n equals to 2k plus 1.
And then you just subtract the n in the equation? I mean, yeah,
You substitute
substitute
it.
the n
You
in the
substitute, right? If n, you let it be 2a or 2k, you just substitute n into 2k.
and for
If
the
it's
odd, it's just 2k.
2k plus 1, right?
Okay, thank you.
You're welcome. Looks good, Samuel. Looks good, Shamisha. That's for n equals even, the even case. Moises, did you just copy and paste? Okay, if not, it's perfect. Okay, I done 2a squared is 4a squared. 4a squared times 3, that's 12. Oh, okay, I see. Okay, hold on, that's mistake, Moises. I know, it's not copied. 3n squared. It's a typo. What's 2a squared? 2a squared is 4a squared. 4a squared times 3, that's 12a squared, right? Just a little typo. 12a squared plus 2a plus 14. So a small typo there. So 3, let me write this term. 3, 2a squared equals to 12a squared. All right, a couple of you made a mistake. The 2a times 2a is 4a squared. 4a squared times 3, that's 12. 12a squared. Huh, all of you made the same mistake? That's interesting. Aidan has 6a squared. Aidan, do you see the mistake? It's 12a squared. Patrick also have 6a squared. Maria? Okay, just type in the number. You don't need to type in the whole question. Right, Moises, right. You copy and paste from your Microsoft Word. Okay. Okay, my Wu's odd case looks good. Okay, Xiaoming's looks good. All right, I think we get the idea of it, right? I just don't see Nino's. Nino, Patrick, Shamisha, Jinqi. You know you have participation credits, right? So make sure you participate so you can get credits for participation. Oh, okay. If sometimes you read on your paper, you may, if you want to share, you can share on your screen. Why not use a computer? You know, like Moises is using Microsoft, right? There's so many Word files you can use. Nowadays, we don't really need a pen or pencil for some, right, for stuff like this. Oh, Shamisha, you shared? I don't see yours, Shamisha. Oh, you shared even case, right? Okay, I see. Okay, Jinqi, what are you confused from?
Why are we using the 2k plus 1 or like the 2k?
Oh, okay, you see for E, right? E is saying for N is an integer. We want to prove this is even. But then there are two cases in the integer, right? In the integer, N can be even, N can be odd. That's why N even we can write as N equals 2k. Odd we can write as N equals to 2k plus 1. That's the definition of odd and even. Make sense?
Okay.
That's right. So the 2 is a factor in the end because it's a 2 times something. And the something is an integer. Right? 2 is a factor of the result. So it's it proves it's not even. That's right. Since it multiplied by 2, since 2 is a factor of it, it's even. So this E can be divided by into two cases. Oh, I then let's see. What do you mean? Let's see. What did you write? Right, you read it, right, suppose n is even, right, n can be written as 2a. Right, you see 2a squared is 2a times 2a, which is 4a squared. 4a squared times 3 is 12a squared. So what you wrote 6a squared. So you're missing, so 6 is a typo, it's supposed to be 12. Right, to prove the odd case, you just write n equals to 2a plus 1. In the end, you also see the result has a 2 as a factor. All right, anybody has any questions? Okay, so we have a couple more questions. We have this A, B, C, D, then we'll be done. So let's show A. A is in X is an even integer, right? So we don't have to divide it into two cases anymore. We show this x squared minus 6x plus 5 is odd. So that means we can write as 2 times something plus 1. That's definition of an odd integer. Okay, let's try A, B, C, D. Right, Maria, you need one more step. You need to write down this result. You can do 2 times. You can split 21 as 20 plus 1. Then you have 12a squared. Let me write here. So you have 12a squared plus 14a plus 20 plus 1, right? You want to split as this. So the first 3 terms, you can factor out 2. Then you write as 2 times 6a squared plus 7a plus 10 plus 1. Now you see this is in 2k plus 1 form, where k is the integer. K is 6a squared plus 7a plus 10, which is in integer z, right? So Maria, you need to finish writing down more lines like that. My U is saying, okay, even x is even, da 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 da. Okay, my U is proving 8, 1, 8. So writing x as 2x. So 2x squared minus 6 times 2x plus 5. That's in the end is 4x squared plus minus 12x plus 5. So factor out 2. Then that can be written as 2 times some number plus 1. So that's to show it's odd. Good. Jinqi, right? Writing x as 2a plus 1. Then simplify it. You need to simplify it in the end, write down as 2k plus is in the 2k plus 1 form, and k is the is in integer. Right, looks good. Maya's looks great. So in the end is 2b plus 1, while b is in z. Great. Yes, that's a perfect proof. Patrick, what do you mean 4k squared minus 8k plus 6? What do you mean by that? Yeah, for some of you, if you finish the 1a, try b, c, d. Right?
Like
Yeah.
I replace the x with 2k plus 1, and then I
Which
work for...
one are you talking about? Are you talking about, Patrick, are you talking about 1a?
Yes, ma'am.
1a, x is even. You can write x equals to 2k or 2a. Do you see that? X is even. X is given as an even integer.
Oh, I thought we were trying to prove that x squared minus 6x plus 5 is odd. Like I'm a
Yeah,
little
we're trying to prove that. We're trying to prove that is odd by assuming x is even. You see, if p, then q.
Okay. I understand now.
Okay, all right.
So if x is 2a, then if we put 2a in the equation, then it should come out as odd.
Exactly.
Oh, okay, thank you.
You're welcome. Okay, Lino write 2K. Jinqi, you only write the solution. You need to write down the steps, right? Oh, I see. You have 4a squared minus 2a plus 7, right? Then you said, okay, that can be written as 2 times this plus 1. Perfect, yes. Let's see, Nino's 2k, right, in the end, that's really 2 times that plus 1. So it's in 2k plus 1 form, which is odd. Great. Nino's great.
Professor?
Yeah.
So even when you plug the 2a in and you get your final final expression, you're still supposed to be able to factor out 2, right?
Factor out 2 times something plus 1.
So
2k plus 1.
So if I have, wait, 2k plus.
It has to be 2k plus 1 form to show it's odd. Does it make sense?
I have 4a squared minus a plus 5. So
That's right. The 5 can be split into 4 plus 1. So the first 3 terms with 4, you can factor out 2. Maybe you can see someone's answer in the chat.
Oh, okay, thanks.
Yeah. So 2k plus 1 form is odd number. And if we write something as a 2k, k is an integer. That's even. That's the definition of even and odd. Okay, looks good. Moises looks good. I then, let me see, x squared. Right, then you need to keep doing. So you have 2a squared minus 6 times 2a plus 5. Yes, simplify that. In the end, write down as 2k plus 1, write in a 2k plus 1 form. K is some expression. Michael, 4a squared minus 12a, you don't get 12a anymore. Oh, hold on. 4a squared minus 12a plus 5. That's right. So 2 times 2a squared minus 6a plus 4 plus 2, right? Michael, you see plus 2, because you already factored out 2, plus 1.
Professor.
Yeah.
I got the same thing as Moises. I guess I'm just confused as how he did like the last factor step.
Okay, you see this one. He wrote as 2 times. Can you see my highlight under Moises in the chat?
No, I was looking at Moises' thing.
Okay, let me copy this. Okay, I typed under my name in the chat.
Oh, I get it. That's what you mean by separating the 5 into 4 and 1, so you can factor the 4?
That's right. You can factor out 2,
okay.
4. Yeah.
All right.
So now you see you are in 2k plus 1 form. And this k is inside the parentheses.
Yeah, the k just represents the entire parentheses expression.
Exactly.
Okay, thank you.
You're welcome. Okay, let's see. Ajaya, when I simplify 4k squared minus 12k plus 5 is 2k squared. No, Ajaya, you need 2 outside the parentheses. Ajaya, let me see. Anything else you're typing in there? Basically, right. Basically, you can check. What Moises did under my name. I copy paste his answer. All right. So he let x equal to 2a. You just substitute x into 2a, then you do the calculation. Then you do the calculation, you have 4a squared minus 12a plus 5. And you want to write down as 2k plus 1 form. So you split 5 into 4 plus 1. Then you factor out 2 from the 3 even terms. So you have 2 times inside the parentheses. Well, whatever inside the parentheses, you can treat as a k. It's an integer, right? So you have 2k plus 1. As long as you can write something as a 2k plus 1 and k is an integer, that proves that's an odd number. Oh, Aidan, what do you want me to repeat? Which step? You see, under my name, I copy paste Moises' answer. So he let x to be 2a. So an even number means we can write the number as 2 times an integer. So k is an integer, or no, I mean, sorry, a. A is an integer. So x to be even means I can write x equals to 2a. A is just some integer. So then we simplify the expression. Then in the end, we write as 2 times something plus 1. And this something we can think as k, 2k plus 1 form. Patrick is asking if we didn't have the 1, that would prove it's not even number. That's exactly right. So the definition of even number is 2 times an integer. Odd means 2 times an integer plus 1. That's the definition. Where does the 2 in the parentheses come from? Let me see. We factored. You see 4a squared minus 12a plus 5 can be written as 4a squared minus 12a plus 4 plus 1. Because 5 can be written as 4 and 1. Does that make sense? Aidan, do you see that? Split 5 as 4 and 1. So see, then the first 3 terms, let me just type in the chat. The 5 split into 4 and 1. I'm typing in the chat. Instead of thinking 4a squared minus 12a plus 5, think as plus 4 plus 1. Then the first 3 terms, we can factor out 2. Right? We factor out 2. Then with parentheses. Oh, okay. That becomes 2. That becomes 6. That becomes 2. That's a trick. So just rewrite the expression. All right. Any other questions? Okay. Can anyone prove 1b? So if A, B, C are integers, A divides B, A divides C, then A divides B plus C. I subtract 1 from 5 and add the 1 outside in order to divide it evenly. Okay.
Professor, did you forget to put the 1 in the last thing you posted or pasted?
Yeah, I was just explaining to.
Okay.
Right.
Okay.
So I done what did I do with the first 3 terms? Right, they should be at 1 in the end. Right, the end answer should be this plus 1. Okay, this lecture is very important and probably is the most difficult one, but you have time in this weekend. So make sure you practice on this. Okay, this chapter is very super important of this course. What we can see is the core of this course. You know, to be able to prove something. Okay, Ajaya, do you have questions? I see what you wrote, 4k square. Right, you're thinking x as 2k. That's right, your answer is right, yes. Okay, Maya is writing 1b. So we want to show a is a factor of b plus c. So a divides b means b can be written as ad, like d is some integer. And a divides c means c can be written as be, and e is some integer. So a divides b, a divides c, a divides b, right? A divides b, a divides c. A divides b, a divides c. Maya, we don't have b divides c though. We don't have a b divides c. I think you might look at the wrong things. A divides b, a divides c. We don't have b divides c. Do you see a mistake? C cannot be written as be, because we don't have b divides c. Right. You can write so b is ad, c is ae. So both has a as a factor. So ADAE. You don't need ADE. Just change a little bit. Your answer will be right. Okay. A divides B means A is a factor of B. So B can be written as AD. D is some integer. A divides C, that means C can be written as AE. E is some integer. So then B plus C equals to AD plus AE. That's A, we can factor out A, that's A times B plus C plus D plus E. Right, D plus E is just some integers. So A is a factor of C. So that means A is a factor of B plus C. That means A divides B plus C. Does it make sense, Ajaya? E is just some number. You know, E is some integers. Think about, okay, let's think about the two numbers. 3 divide the 6, right? Then 3 divides 9. So we want to prove 3 divides 6 plus 9. You see, in this case, 3 divided by 6, because 6 can be written as 3 times 2. So in our case, means A divides B. That means B equals to A times some number E. We don't care, you know, what E is, but the E is an integer. A divides C. It's like 3 divides 9, right? 9 can be written as 3 times 3 in this case. So A divides C. That means C can be written as A times some other number, right? Maybe D. call the number d. D is just some integer. So now what's b plus c? B plus c equals AE plus AD. We can factor out A. So A times parentheses E plus D. So to prove, that means we use some general notations. We don't want to use a real number. Let me write down in this case. So A divides B means we can write down B equals to AD. You know, for some for D in integer. And A divides C means C equals to AE for E in integer. Okay, I'm typing in the chat. So what's B plus C? B plus C equals to AD plus AE. So we can factor out, that means B plus C equals to A times B plus E. We factor out A. Right, what does this mean? This means A divides B plus C. That's the proof. If ABC is too abstract, you can think some numbers to work with. Okay, last one, not last one. So when C is proved is an even function, right? So we want to plug in negative x into the function. We want to show negative x. After the calculation, we see, the simplify the result still the function g of x. So g of negative x equals to g of x means this function is even. The last one, 1D, if two integers have opposite parity, that means we write down one, maybe one as an integer, right? One as an even, the other one as odd. So maybe, one we can write as 2a, the other one we write as 2b plus 1. So 2a is an even number, 2b plus 1 is odd number. So we want to show that product is even. So we just multiply those two. So 2a times 2b plus 1. What do we get? We get a 4ab plus 2. Well, we factor out 2. Go 2ab plus 1. That's in the definition. So we get 2 times something. 2 times an integer. That's in the even form. So which proves this is an even number. All right. Any questions? Okay, so this lecture has a lot. So the good thing is you have an extra day to work. You have a weekend and a long weekend to work with this material. All right. If you still have questions, we can talk about it on Tuesday. And I know you have some questions for homework 7. I'm going to post the solutions for homework 7. And if that answers your question, that's good. If not, we'll talk about them on Tuesday also. Okay. I guess I'll see you on Tuesday, and a happy long weekend. Thank you.